Good day, viewers. This is Ademola Johnson, your science tutor. Now, in this area, we have been dealing with electronic configurations and the rules governing electronic configuration. We have talked about Heisenberg or certainty. We have talked about Aufbau principle. We have talked about Hund's rule of maximum multiplicity. Lastly, we are looking at Pauli Exclusion principle. What does this principle state? This principle states that no two electrons in the same atom can have the same value for all the four quantum numbers. No two electrons in the same atom can have the same value for all the four quantum numbers. Let's take a look at, for example, for instance, in the atom of which element can we use? Of beryllium, Be drawn below. Let's check. Beryllium Be, which is a 1, 2. 1, 2. Now, let's look at this. This is the atom of beryllium. Okay, let me say, okay, this one is 1, 2. This is the nucleus. This is K shell. And this is L shell. Now, no two electrons. Let's consider this electron in L shell and one electron in K shell. Already they have different principal quantum number. One electron in K shell and one electron in L shell already have different principal. Already have different principal quantum number. Why? As the principal quantum number, small letter m, for electron in K shell is 1, while the principal quantum number for the electron at the L shell is 2. So we have studied that for K shell n equals to 1, but for L shell n equals to 2. So they already have, there are 4 quantum numbers. Already, the two of them have different principal. Then they will be different in azimuthal. They will be different in magnetic. They will be different. They might be different in spin or equal. It depends. Now, but the 4 quantum numbers of the 2 electrons are not the same. Then considering the 2 electrons in the in the same atomic shell. Now, these two electrons, this one now and this one, occupying K shell, can they have the same value for all the 4 quantum numbers? Then, what are we saying? They have similar value for only 3 out of the 4 quantum numbers. But when it comes to spine quantum number, spine quantum number S, one of them has +1/2 as it moves clockwise, while the other has -1/2 as it moves anti-clockwise. So this one now, if it moves clockwise like this, then this one will move anti-clockwise. So that is why when we're representing with Uzru, beryllium Be4 was represented as 1s2 and what? 2s2. You can see that, and the two of them occupy what share now? The two of them, now this is this is a K share, while this one is what? L share. So you will see that the two electrons that are in the same share now, they have different spine quantum numbers. One is moving clockwise, the other one is moving anti-clockwise. So they are the same elements occupying the same shell. The two electrons occupying the same shell, atomic shell, have the same principal quantum number, have the same azimuthal quantum number, have the same magnetic quantum number, but when it comes to spine quantum number, they are different. Why? Because one will move clockwise, while the other one will move anti-clockwise. Then what do we mean by quantum number? Let's now talk about quantum number as a topic. Quantum number. What is quantum number? Quantum number. A quantum number is a mathematical value. Just a value, is a number that determines the shape, it determines the orientation and the energy of electrons orbitals in the atom of elements. That's the definition of quantum number. Quantum number is a mathematical value. It's a number. And it does 3 things. It determines the shape. It determines the orientation. And it determines the what? It determines the shape, the orientation, and the energy. The energy of the orbital containing what? The electron. Now let's look at types. Types of quantum number. Now, there are 4 types. There are 4 types of quantum number. Now, what are they? These are 1. Principal quantum number, which is denoted by small letter n. 2. Azimuthal or subsidiary quantum number. That's L. We use L to represent it. Now, then the next one, it might not be L, but it is symbol looking like L. But I don't think it is English letter. So take note of that, the symbol. Now, number 3 is magnetic quantum number, which is denoted by MS. And lastly, we have spin quantum number, or you call it spin. So let's take them one by one. Principal quantum number. Which is denoted by small letter n. So principal quantum number is denoted by small letter n. So take note of that. Now, what is principal quantum number? This is the number that determines 2 things. Determines they determine 2 things. Number 1, the maximum number of electrons occupying an atomic shell using the formula 2n squared. Don't forget we have used this formula to determine that. So, for instance, K shell can hold the maximum of 2 what? Electrons, as n equals to 1. Then you have 2 into 1 square, which is same thing as what? 2 into 1 times 1, which is same thing as 2 into 1, which is same thing as 2 times 1 is what? 2 electrons. So that is principal quantum number. So then another thing it does, it is also used to determine the number, the total number of degenerate orbitals present in an atomic shell using the formula n squared. For instance, For instance, in M shell, where n equals to 3, then we have how many? We have, let's check, n, that's a 3 square, which is equal to 3 times 3, which is 9. We have 9 degenerate orbitals. We have 9 degenerate orbitals. How? Nine degenerate orbitals. How? Let's check that. In M shell, we have, what do we have? We have, M is number 3 now. We have 3s orbital, 3p orbital, we have 3d orbital. And this one has only one degenerate. One degenerate. As you can take 2 electrons. This one has 3 degenerates. What are the 3 degenerates? That's px, py, and what? And pz. So then 3d has how many? 5 degenerates. So add up these 3 numbers, you have 9. 9 total number, 9 total number of what? Of degenerate orbitals in M shell. So in general, the principal quantum number of K shell, M shell, and N shell is 1, 2, 3, and 4 respectively. What am I trying to tell you? The principal quantum number for K shell is 1. Principal quantum number of N shell is 2. Principal quantum number of M shell is 3. While that of N shell is what? Is 4. So can we go to azimuthal? Azimuthal or subsidiary. Quantum number. This is represented with this letter. Now, this is the number. This is the quantum number used to determine the energy level, of the orbital containing the electron. So this is to determine containing what? The electron. Then take note. The azimuthal if the azimuthal quantum number is 0, 1, 2, and 3. Then the electrons occupy S, P, D, and F orbital respectively. What am I trying to say? There is a formula I'm going to give that we use to calculate azimuthal quantum number. And if your answer is 0, it means that the electron, that orbital is what? S orbital. If your answer is 1, it means it is P orbital. If your answer is 2, it means it is D orbital. And if your answer is 3, it means it is what? F orbital. And the formula is this. So azimuthal quantum number is determined using the following mathematical formula. What is the mathematical formula? L is equal to 0 dot 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 n minus 1. That's the formula. L equals to 0 dot 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 n minus 1. Now let me show you what I'm saying here. For example, serial number. You have atomic shell. You have azimuthal. You have principal quantum number. Principal quantum number, which is n. Then you have azimuthal quantum number, which is L equals to 0 dot 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 n minus 1. Yes. Now, the first shell we have is K shell. K shell, principal quantum number is what? Is 1. Then what is the azimuthal? Azimuthal must begin with 0 and ending with what? Because why is it beginning with 0? If you have n minus 1, 1 minus 1 is what? 0. So that's what you have here. So number 2 is L shell. How did I get it 0? N, your Ni is 1. Put 1 inside here. 1 minus 1 is what? 0. So no need of putting 2 zeros. Put 1. So now, L shell, principal quantum number is what? Is 2. If it is 2, azimuthal must begin with 0 until it gets to n minus 1. So that means, if you have that, that means what? 0. Begin with 0. What is your n? N is 2. That's 2 minus 1. So that shows what? 0, 2. 2 minus 1 is 1. So that is 0 and 1. Your answer will now be 0 and 1. 0 and 1. So that is that. So 0, this 0 is this 0. 1, 2 minus 1 is what? Is 1. So 0 and 1. So 0 and 1 is what? Is the azimuthal quantum number. Then number 3. And that shows that as we are getting 0, it belongs to S orbital. As we are getting 1, it belongs to P orbital. So take note of that. Number 3 is M shell. M shell, principal quantum number is 3. Then azimuthal is 0 dot 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 n minus 1 dot 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 3 minus 1 0. Why dot 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 means there is a continuation. Let's 3 minus 1 is what? Is 2. Between 0 and 2, what is the number in mathematics? That's 1. So now M share now contains what azimuth? 0, 1, and 2. Now, mind you, this one, because L share, this is what? S orbital. What type of S orbital? 1s orbital. That's what it contains, because the principal is 1, this coefficient. Now, what type of S orbital is here? 2s and 2p. Don't forget, before we have said that L share contains 2s and 2p. Then this one now, this one is 3. So this one now contains what? 3p, 3s orbital. We have for 1, we have 3p orbital. For 2, we have 3d orbital. So we have said that M share contains 3 spd. We said that K share contains ordinary s. We say L share contains sp. The other one contains spd. So the last share here, that's N share. Principal quantum number is 4. So if we are to do that, you have 0, 1, 2, and 3. And when you get that, this one means what? 4s orbital. This one has what? 4p orbital. This one has what? 4d orbital. And lastly, here you have what? 4f orbital. So that is that. So we are going to stop here, and in the next video we are going to look at magnetic quantum number and spin quantum number. So take note of that.